Thank you very much for the opportunity to present today. So I'm going to be talking about experimental push-out tests on stainless steel headed stud shear connectors, which is part of my PhD research at the University of Southampton. So I'll give you an outline of what I'll go through. So I'll begin with a brief background into my research topic, which is stainless steel composite bridges, and I'll then discuss the test program that's being carried out, beginning with simple tensile double shear tests on the connectors and progressing to welded tests and finally the full-scale push-out tests. We then compared the experimental data with predictions from international design codes, and I'll end with some conclusions. So I'm researching stainless steel composite bridge beams, and the main reason for this is the excellent durability advantages offered by stainless steels due to the corrosion protection, and this can lead to very significant lifetime cost savings over the life of a bridge structure. Stainless steels also have very high strength and ductility, so there's additional performance advantages there. Within my research, I'm focusing specifically on welded shear stud connectors. So we can see from this diagram here that they provide the composite connection for composite action between your steel girder and your concrete deck. Now, if you're swapping out your steel girder for a stainless girder, you actually have, or we're exploring two options for your shear connection. You can have a stainless connection on your stainless beam, but also because of the protection provided by that concrete encasement, there's a degree of insulation from that. We're also exploring carbon steel studs welded to a stainless steel beam, which is a way that you could potentially bring those costs down because stainless is slightly more expensive than carbon steel in upfront costs. Now, despite the potential advantages of stainless steels, there is very limited knowledge and performance data on the shear connectors. And so this is kind of a review of the existing codes that are out there and whether they are applicable to stainless steels or whether new codes are needed. To begin with, we carried out some simple material tests on the stud connectors. So we machined out some tensile coupons and also some shear rods and tested those to kind of give us our material behavior profile. And particularly the shear results kind of give a lower bound capacity of what the behavior in a push-out test would look like. We can see that both of our stainless steel grades are stronger and much more ductile than our carbon steel stud, and they also have a lot of strain hardening and a kind of non-linear response, which is what makes stainless steels unique. We then progressed to doing welded stud tests. We wanted to see if there were any detrimental effects from the welding process, particularly if we were welding the carbon steel to the stainless steel beam. There might be some annealing or something going on, so we wanted to check that. Now, the austenitic grade of studs and the carbon steel studs can be automatically arc welded, but the duplex can't. They have to be fillet welded, which is a limitation on that kind. So we only carried forward the carbon and the austenitic for these series of tests. And these were welded to a lean duplex grade of plate, and this was the same that was used in the beams in our push-out test. So we automatically welded the studs and then sliced the head off so that it could be gripped in our test rig and carried out the same tensile loading protocol as our coupon tests. And the data from the coupon tests is shown in blue on the graphs, so that kind of shows the underlying material performance for our carbon steel studs and our austenitic studs. And then in terms of the welded tests, we observed two failure modes. So there was brittle failure at the weld and ductile failure in the shank of the stud. Now, we didn't observe any annealing effects or anything like that. So all of the specimens do lie on top of the stress strain curve from the tensile test. So that's good. However, we did observe one of the carbon steel specimens and 3 of the austenitic specimens did show that very brittle weld failure. In particularly the carbon steel specimen, you can see fractured at very, very low strains. The austenitic specimens, most of them still reached their ultimate capacity, and even the ones that failed early still had a more reasonable amount of strain prior to failure. But there was a lot of irregularity going on here, so we wanted to try and take a closer look and see if we could get more information about what was happening in the welds. And so we first of all carried out some X-ray CT scanning of the welds to try and have a look through the cross-section. And immediately we noticed, as you can see on the left, the carbon steel specimens had a significant number of voids present in the cross-section of the weld, which was quite alarming to see. We compare that to the austenitic specimens, and the cross-section where the stud is bonded to the plate is much more uniform. There are some very slight hairline gaps that we can see. around here. So perhaps they haven't fully bonded along the diameter of the stud, but definitely much better than what we can see in the carbon steel specimens. I've also shown some extracts from the DIC camera data that we extracted during the tests, and we can see that there are stress concentrations happening at that weld interface. Another way of investigating them was to carry out etching and microstructure analysis, and this revealed a very high presence of martensite at the weld between the carbon steel stud and the lean duplex beam. And now martensite is very brittle, but it is stronger than the base stud material. And so this explains perhaps why, despite all of these voids that we see, most of our carbon steel specimens still reach their ultimate strength. But there was kind of an unpredictability to it, and sort of visually the quality of the welds is not ideal. So we then progressed onto our full-scale push-out tests, following a method that is outlined in Eurocode 4. So if you're not familiar, you basically sandwich your steel beam in between two concrete slabs. You've got your shear connectors welded to the flanges, and then you load down the center of the beam so that you are testing your connectors in shear. And the code gives a series of predictive equations for evaluating the capacity of your shear connectors. And that's the minimum of these two equations, depending on whether your failure is governed by stud failure or concrete failure. So stud failure depends on the ultimate strength of your stud connector and its diameter, whereas concrete failure, again, is stud diameter, your concrete properties, and this alpha factor, which relates to the height to diameter ratio of your stud. And effectively, that's applying a reduction for very short studs due to the increased likelihood of having a pry-out failure. There are some limitations given by Eurocode 4. First of all, these equations are only applicable up to studs with an FU of 500 MPa, and already our austenitic studs, they have about 692 MPa. So we're already pushing the scope and the limits of Eurocode 4 with these tests. And another key aspect is that for full shear connection, studs need to have this characteristic slip value of 6 millimeters, which is evaluated as a certain point on your descending branch. So this is what our specimens looked like. We embedded them in some dental plaster and we stuck LED trackers onto them so that we could use a camera system to get our load slip response. And in terms of the materials we tested, so we had our carbon steel studs on lean duplex and we had our austenitic studs on lean duplex. And the first series of tests we did for each was embedded in a C100 concrete. And the reason for choosing such a high strength concrete was because we wanted to observe stud failure and steel failure. And given the high capacity of the studs, that meant we needed an even higher strength concrete so that we weren't just getting premature concrete failure. But after that first series of tests, we then ran a repeat with our stainless austenitics in a weaker grade concrete to see what difference that may make. So our results are shown here for the 3 series of tests. Now, all of the specimens exhibited stud failure, even in the C50 grade concrete. And we did then split the specimens apart at the end to have a look at what was happening to the steel and the slab. So it should be noted that we had to force them apart at the end. So the fracture in these images isn't completely representative of what happened during the test, but it gives a really useful indicator, particularly in terms of the concrete crushing is quite limited and localized, even in our weaker specimen here. And particularly in our carbon steel specimen, we can actually see the voids within the weld itself, which was interesting to see. In terms of the load slip response, there was a sudden drop in load in one of the carbon steel specimens when one of the studs failed very early on. And there's actually a lot of scatter in the level of ductility within those tests. There was also a sudden fracture that we observed in one of the austenitic tests, but this happened after the peak and so wasn't cause for concern. So we evaluated our results numerically as well, and the ductility of the carbon steel studs actually came out as 3.1, which is significantly lower than that 6 millimeter requirement in Eurocode 4. So for that reason, and combined with the observations we made during our welded tests, we concluded it's not viable to be using those carbon studs on stainless beams. However, very promisingly, our austenitic studs were very strong and very ductile, and so they can definitely be carried forwards. So as well as looking at Eurocode 4, we looked at some other international design codes, so American, Japanese, Australian, and Canadian, and they all have a very similar format, but perhaps use slightly different coefficients or different resistance factors. So we compared them numerically and graphically. We set all the resistance factors to 1 for this purposes. And we can see that most of them accurately predicted that there would be stud failure, but some of the codes incorrectly predicted concrete failure for the weaker series of tests, even though we did actually see stud failure. So Ashto 9, the Japanese and the Canadian, they incorrectly predicted the failure mode and they were quite unconservative.
It's 10 minutes, Rebecca.
Okay, I'll just rush through. But the rest of them were on the more conservative side. We've compared them also with data from the literature, so carbon steel studs on carbon steel beams, and we observed similar trends. And so overall, our conclusions were that the austenitic studs can be classed as ductile and they have high resistance. The carbon steel studs can't be considered ductile. There are a lot of voids and presence of martensite in the weld. Generally, design codes are very conservative, and I'm carrying out extensive parametric modeling to kind of broaden that data set so we can actually do statistical reliability analysis on the codes. Thank you very much.